So I will talk about the DOOP framework. I'll give you a quick introduction of the DOOP framework. Let me share my screen, and I think it should be fine now. Oh, okay.
Yes, we can see it.
Yeah, not the right way. Screen sharing. Let me share the window instead. No, maybe not. Sorry about that. Give me a sec. Okay, so should be fine now. So I'll give you a quick presentation of the DOOP framework. It's more of an advertisement of the whole framework, although we will see some command lines, so you will get to see a little bit of how to use DOOP. And if you're interested, please ask me questions. Ask me questions over the Slack channel. So just interrupt me even if you want. I'm not going to be watching the Slack channel while I'm presenting, but if you are a panelist, feel free to interrupt me. It's much more lively that way. So DOOP is an artifact of work for over 10 years. Originally, it was the work of my postdoc, Martin Bravenboer. He created the first version, and lots of people have maintained it and enhanced it since. It is a declarative framework. It is also a representative of many other frameworks that I've worked on since basically 2008. DOOP is our foremost example of declarative static analysis. It was originally a pointer analysis framework. Now it includes many other kinds of analysis, but they all have the same basic form of value flow analysis. And pointer analysis plays a very big role. And taking DOOP as an example, we've had several offshoots. So we've had another framework, Kleiser, for LLVM bitcode, and frameworks that Bernard earlier alluded to for analyzing Ethereum smart contracts like GigaHorse and MadMax. So pointer analysis, or generally any static value flow analysis, is a domain of complex mutual recursion. The main relation, the main result one wants to compute is something that we might call var points to. What values a variable may point to, or what values a variable may hold, if you want to think of constants instead of pointer variables and abstract objects. Now, as you all know, modern languages have indirect calls. They have virtual calls or first-class functions. So there's mutual recursion between constructing a call graph and computing points to information. So unless we know what value a variable can hold, we don't know what a function call will end up calling for real. So that's the dependency of call graph to points to information. And of course, the other way is a very simple dependency, because if we don't know what code we're calling, we cannot even compute the values for all variables. The same kind of mutual recursion exists between all sorts of different sub-analyses. So we can think of analyzing dynamic features of a programming language. Like in Java, we have dynamic proxies and other dynamic loading techniques. We have reflection. All of that, the best techniques that have been proposed for analyzing them are in mutual recursion with the base analysis of value flow through the program. Now, what we would like to do is encode all of these little boxes separately, but we want to have them interact as seamlessly as possible. So that's roughly the goal of DOOP. And one can think of DOOP in a way of holistic program analysis, to borrow the slogan of Douglas Adams's Dirk Gently, the holistic detective. Everything is connected. So DOOP is not trying to do one kind of analysis, not trying to do specifically taint analysis for a specific kind of vulnerabilities. It's trying to give you an over approximation statically of everything a program can do. And it builds on the philosophy that everything is connected and everything should be modeled in parallel, but with interesting interactions. If you think of it that way, Datalog becomes a great avenue for expressing what we want to do. Datalog is a programming language that's really based on logic. It's very much logic with a little bit of computation, logic with recursion. And it's equivalent to first-order logic over finite structures. You can think of it as SQL with full recursion. If you like thinking about databases, you can think of it as Prolog without ways to construct objects, although in practice, we do construct objects in most of the Datalog variants. DOOP right now is using Souffle as its Datalog backend, as you just heard. And Souffle does allow construction of objects. So effectively, we do have a Turing-complete language, but most of everything we express, most of our algorithms are in a subset of the Turing-complete language that is equivalent to polynomial time computation. So we take inputs as tables and we combine those inputs. And for most of what we do, we have a guarantee of polynomial time complexity. Now, Datalog as a language is strictly declarative as opposed to Prolog. So we can reorder any clauses in the body of a rule, or we can reorder the evaluation of any rules, and we are guaranteed to get the same result, maybe not in the same time, but the same result semantically. And it enforces strict guarantees of monotonicity. In a way, it is less programming and more specification. It's very much a specification language, a logic-based language, and less of a programming language. So let me give you an idea of how we express interesting static analysis algorithms in Datalog. We have the program. We have our input program. We represent it as a database. What does this mean? Well, first, we get some tables, like table alloc here and table move. And the tables encode the instructions of the original program. In DOOP, we actually encode pretty much all the instructions of the original program, but many algorithms do not use most of the tables. So here we know that there is somewhere an instruction. I'm not showing identifiers for instructions. I'm just viewing the table alloc as a set. There's somewhere an instruction that assigns a new object of type A to a local variable little a. And the same for B and the same for C. And also in compiler lingo, we have assignments between temporary variables, and those are called moves. So there's somewhere an instruction that's a move instruction between B and A. Once we have encoded our program as a database, we have little declarative rules. We actually have thousands of declarative rules that express all our algorithms. And the hello world of Datalog computation, of Datalog static analysis, is a very simple transitive closure computation that combines the alloc table and the move table. Alloc gives original values to variables, and move propagates them throughout the program. So here we have two rules. And the syntax is that the rules have a head. Each rule has a head, a connective here, an arrow in Prolog style or in graphical arrow style. And then there's a head relation that's populated on every firing of the rule. And there are bodies to our rules. And the rules are evaluated by taking the body relations, which are really tables, and then joining them together. So the really interesting evaluation here is the one of the second rule. And you can think of this as a database join based on the second column of the move table and the first column of the var points to table. But logically speaking, what does this whole thing say? It says that I know that a variable has a certain value if the variable is directly gets the value at an allocation site, or recursively, a variable 2 has a value obj if I have already proven, and I don't care about how I proved that. It could have been through any of 1,000 different rules. Many are very complicated ones. But if I've already proven that variable from has value obj, and I see a move instruction from to 2, then I know that 2 also has value obj. And here we directly see the recursion that Datalog allows us to express. So with simple evaluation, evaluating the first rule, the var points to relation gets these 3 tuples that we see here, and then joining this table with that, tuple by tuple, we join this one with this one. Now we infer that A can also point to the abstract object allocated that instruction new B. And similarly, we do the same thing until fixed point, and we get the transitive closure of the whole computation. And that's the principle for computing using Datalog. And that principle, of course, we've taken it to great lengths in DOOP. We have, like I said, thousands of rules that encode the semantics of complicated language features for Java. So DOOP is a framework for Java bytecode analysis. The input that we accept is Java bytecode or Android bytecode primarily. We also have a Python subset right now, but it's for a special form of analysis. The core of DOOP is Java or Android bytecode. Everything is declarative. It implements a very rich set of analysis. So we have analysis that satisfy all of these keywords that I'm not going to get into from the points to analysis literature. And it also supports lots of the semantic features of Java. So we model very faithfully JVM initialization, some native methods, things like reference queues, class initialization, finalization. We have a sub module for reflection analysis, all sorts of things like that. Now, to summarize, DOOP makes declarative analysis real. We express highly complex algorithms that are both very powerful and very precise entirely in Datalog. We do not write Java code for the analysis core itself, only we write some connective code outside of Datalog. The core specification right now numbers close to 2,000 rules. Depending on how you count, it could also be more than 2,000 rules. And these are parameterized by a handful of rules per analysis flavor. We have lots of flavors that give you different balances of precision and scalability. And one can think of it as getting highly efficient algorithms from a logic-based specification. And we do optimize that, and one can think of it as heuristics for setting the algorithm space. One can also think of it as giving the right plan directives to Soufflé. So DOOP takes great pain to optimize very, very well its rule execution. So it's a demanding client of the Soufflé Datalog engine you just heard about, and highly optimized in many ways. So this pretty much concludes my advertising presentation of DOOP. And what I'd like to do next is just give you an idea of command lines, how you actually invoke it, and what you see when you invoke it. And I hope if someone can quickly confirm, one of the organizers, that my screen is at sufficient resolution and visible with the terminal.
I can see your screen, but you're technically pretty out of time, and we have a couple of questions. So okay, I think people can see that the terminal works. So
I better take questions. I will just impress you, maybe in a negative way, with the richness of command line flags. Now, this is the DOOP invocation, and these are all the flags that it prompts you to give it when you invoke it. So I'll take questions.
So first question from Arlen Cox. Given the recent disassembly in Datalog work, could much of the DOOP frontend be written in Datalog itself? What costs or benefits might be associated with that?
So I don't think so, because the DOOP frontend does a very straightforward translation from Java bytecode to tables. That's all that the DOOP frontend does. So we do use Soot, but we only use it for fact generation. So it doesn't have any complex static analysis in there. All the work on doing decompilers in Datalog tries to solve a deep static analysis problem in Datalog. So I have some work like that, the GigaHorse decompiler for Ethereum, but also there's the Grammatech work, for instance. There's also work from CMU that uses Prolog for decompilation. So there have been like 3 highly visible decompilers from ultra low level code using Datalog, all 3 of them. But they use Datalog because they try to express complicated algorithms, whereas our front end is a very dumb algorithm. It's a one-to-one mapping from bytecode instructions to tables. So I don't see any benefit in trying to move that into Datalog. There's just straightforward engineering complexity.
Thank you. We have another question, and I think just barely time for that one, from Tamas Sabo from ITEMIS and the Johannes Gutenberg University Mainz. How do you typically go about debugging your DOOP analysis implementations? Some of the analyses are really complex and run on the entire JDK interprocedurally. For this reason, it is often really difficult to find a minimal example that would help debugging scenarios.
So that's true. I mean, for complicated analysis, there are not great minimal examples of input because there's this saying, there are no small Java programs. Like the smallest Java program, if you actually track its execution, there are 7,000 classes, I think, in the JDK that get involved just for a main method that does nothing. So in that sense, debugging is really complicated and one has to have some invariance. This is what I absolutely expect to see at this point, and I watch it very closely to see what it does. One can also create artificial examples. There are some flags here that prevent DOOP from going inside the library that say, stay out of the library, just analyze user level code. And one can create small examples. And finally, small inputs, small programs to analyze. First of all, you probably don't want to go into the library. You want a highly controlled environment. But there's the counterpart of small analysis. And for that, DOOP contains a micro-analysis. And that's only something like 500 or 600 lines. And that's a good analysis for experimenting with new ideas. So those would be my quick answers. But yes, certainly, debugging a complex declarative implementation is non-trivial.